we're going to come up with an algorithm for solving LZ equals B, where L is a unit lower triangular matrix. Why is this interesting? Well, remember that we were trying to solve AX equals B. We could compute an LU factorization of A. Well, not always, but we'll discuss that later. We can then substitute in L times U in for A. We can put some parentheses in convenient places. We can recognize that U times X can be given a symbol Y, the vector Y. And then if we first solve for Y, then later we can solve for X. And all I'm doing here is I happen to change my mind and call the vector Y vector Z instead. Let L be a unit lower triangular matrix. What we want to do is solve LZ equals B, where Z and B are vectors. And this, of course, is the same as solving a lower triangular system of equations, because you can multiply L times Z, and from that then create a system of equations. What we're going to do is we're going to use the exact same techniques that we used to come up with an algorithm for computing the LU factorization to come up with an algorithm for solving a lower triangular system. So we take L and we partition it, and because it's a unit lower triangular matrix, there's a 1 sitting right there. And then we take our vector Z and partition off its first element, and the right-hand side vector B and partition off its first element, and we call those zeta 1 and beta 1 respectively. What did we do last time? We looked at the equation, and we then said, plug this in for L, this in for Z, this in for B. Well, we didn't say that. We did it with A, L, and U, but it's the same idea. And when you do that, you get this right here. And then we multiplied some matrices out. In this case, we're going to multiply out this matrix vector multiplication. And if you do a partitioned matrix vector multiplication, you get this times that for the first part, because this is 0. And then the second part is this times that element plus this times Z2. And then if we look at the fact that this must be equal to that and that must be equal to that, we get these equalities right here. All I've done here is I've said, well, yes, this is equal to that, but what I can do is I can bring this to the other side, and that gives me then this right here. All right, moving right along. We have this now, and the question now is, how do we come up with an algorithm? Right here it says zeta 1 is equal to beta 1. So we know how to compute the first element of vector Z. And then if we go and we update B2 by subtracting off this term right here, then what are we left with? Then we're left with having to solve L2 to Z2 is equal to B2. And notice that going from here to here, I also moved my scalar, which I can always move around to the other side, and therefore you recognize this as an operation that we've seen before. That is an AXB. This then motivates the following algorithm. We march through the matrix L, and we march through the right-hand side B, and at every step, all we have to do is an AXB, where we take the current element of B, we multiply it times this part of L, we subtract that off of B2, and we move on. Recall the algorithm for forward substitution that we got by taking the multipliers, or the Gauss transforms, and applying them after the matrix had already been reduced to an upper triangular matrix. Okay, at that point, all of these multipliers were sitting below A. And if you look at the algorithm for forward substitution, this is the update that had to happen. Now here we happen to have called our matrix A. Here we called our matrix L. But if you go back and forth, you see that they are one and the same algorithm. So forward substitution is simply the same as solving with a unit lower triangular matrix. And we summarize that right here.